Welcome to The Explainer. I am absolutely thrilled you're joining me today because we're about to dive into a literal, mind-bending paradigm shift in off-world exploration. You know, for decades, we've all watched our robotic emissaries slowly, meticulously inching their way across these vast alien landscapes. But what if I told you the era of the slow-motion space rover is basically over? Okay, let's jump right into this breakthrough that is, honestly, about to change everything we know about exploring the solar system.
10 times. That's the massive hook to our story today. NASA's Jet Propulsion Laboratory recently put a brand new rover prototype to the test, and it doesn't just beat the current speed records, it completely shatters them. We're talking about a machine that drives roughly 10 times faster than anything the agency currently has operating on the surface of Mars. Just let that sink in for a second. That is a totally unprecedented leap in off-world mobility.
Now, what's really interesting here is the sheer scale of the contrast. Think about the legendary Curiosity rover. It has been an absolute workhorse for NASA, right? But over 14 years on Mars, it's driven a total of about 21 miles. Now contrast that with our new prototype, named ERNEST. During a recent field test, ERNEST covered 16 miles. But it didn't take a decade, it took 1 week. Specifically, just 37 hours of actual driving time. So ERNEST covered 3/4 of Curiosity's lifetime distance in just a matter of days.
The space speed limit.
So, to understand why this breakthrough is such a game changer, we kind of have to look at a surprising flaw in the multi-billion-dollar machines we already revere so much. They are incredibly, almost agonizingly slow, like 0.06 miles per hour. For a human on foot, that pace would be completely unremarkable. You'd practically be standing still. Out of the 5 rovers NASA has sent to Mars since 1997, Curiosity and Perseverance are the 2 still functioning, and they are restricted to an absolute crawl. But why?
Well, the answer lies in something called the rocker bogie suspension system. This is basically legacy hardware. It's a highly durable, passive geometry suspension system that focuses on one crucial thing, and that's stability. It's actually been used on every single NASA Mars rover since Sojourner landed way back in 1997. And look, it's brilliantly reliable. Opportunity drove over 28 miles over 15 years on this exact system, but its rigid design fundamentally prioritizes staying upright over moving quickly. So if it faces a truly extreme slope or a really awkward obstacle, it just gets stuck. It cannot actively adapt to its surroundings.
Section 2, meet the ERNEST rover.
To break that agonizing speed limit, JPL basically had to rethink the physical architecture of a rover from the ground up. They actually tested 11 different suspension configurations before finally arriving at ERNEST, which stands for the Exploration Rover for Navigating Extreme Slope Terrain. Work on this ambitious 4-foot-long project actually started back in 2022, and it was initially funded just by JPL's internal research and development budget. It was essentially an internal bet that they could build a better, faster, and just much more adaptable machine.
You can actually see the physical departure right where the metal meets the road. Legacy rovers use rigid aluminum wheels, and if you followed the Curiosity rover at all, you probably know those rigid wheels have taken a massive beating on the jagged Martian rocks. It's caused quite a few headaches over the years. ERNEST completely ditches those for flexible mesh wheels, which gives it a totally different profile for gripping and surviving really harsh, unpredictable ground.
Section 3, rethinking rover hardware. But it's not just the wheels that changed. It's the entire philosophy of how the machine holds its own weight. ERNEST features an active suspension system with a brilliant clutch mechanism. This allows the rover to toggle on the fly between 2 distinct modes. In passive mode, it conserves energy when it's driving over nice, flat, easy terrain. But when things get rough, it toggles into active mode. Because it has 2 power joints per wheel, ERNEST can actually lift individual wheels over steep obstacles. Honestly, it can even drive sideways.
I absolutely love how JPL describes this. They say the rover switches between squirming, wheel walking, and obstacle climbing modes. It sounds almost biological, doesn't it? Like instead of a stiff, rigid cart just hoping its wheels don't get caught, you have a machine that behaves like a living creature, squirming and stepping its way out of trouble. It personifies the machine in such a cool, tangible way.
Section 4, AI software and navigation.
But incredible hardware is really only half the battle. The second major hurdle making legacy space exploration so painfully slow isn't physical at all, it's digital. When we communicate from Earth to Mars, there is a signal delay of between 4 to 24 minutes each way. Current rovers run on highly cautious navigation software. They essentially have to drive a few feet, stop entirely, take pictures, beam them back to Earth, and wait up to 48 minutes for a human operator to say, "Okay, the path is clear, move forward another 3 feet." That communication bottleneck is a massive, massive speed killer.
So, to let ERNEST truly run wild, JPL had to give it a brain capable of making its own rapid decisions, and they solved this by using reinforcement learning in their virtual simulation lab. Before ERNEST ever touched a single grain of real sand, JPL pre-trained it for thousands of virtual driving hours across procedurally generated terrain. Because of this intense AI training, ERNEST can decide exactly where to place its wheels on the fly entirely on its own. No waiting for a human on Earth to micromanage every little movement.
Section 5. The next lunar leap.
All of this amazing engineering sets the stage for the actual real-world stakes. What does the speed and agility actually unlock for our future off-world missions? Well, to prove ERNEST was ready for the real deal, JPL put it through a rigorous testing timeline. Phase 1 was right in their own backyard at the Mars Yard obstacle course in Pasadena. Phase 2 moved out to California's Colorado Desert for a much more realistic trial across natural, totally unpredictable terrain in March of 2024. But Phase 3 is where it gets really fascinating. They ran the rover in complete darkness. Why? To explicitly simulate the dim dusk and dawn conditions of the lunar South Pole.
So the crucial takeaway here is that this active suspension doesn't just mean we get to the same old places faster. It means we finally get to explore entirely new, highly extreme environments where legacy passive rovers would just get hopelessly stuck. We are talking about scaling steep, imposing crater walls, diving deep into undiscovered subsurface lava tubes, and navigating the permanently shadowed regions near the lunar South Pole where highly valuable water ice is believed to hide.
Speed is the ultimate asset here. NASA is increasingly relying on commercial partners to lower mission costs, and time is literally money. At the lunar poles, sunlight and power are extremely intermittent. You have incredibly tight operational windows. A fast rover like ERNEST allows NASA and its partners to maximize those windows, covering the absolute maximum amount of ground before the sun sets and the power cuts out.
Now, I do have to give you a realistic caveat here. ERNEST is still a prototype. It is not yet a flight-qualified vehicle. And let's be totally honest, the engineering gap between running a successful test in the Colorado Desert and surviving the violent shaking of a rocket launch, a fiery atmospheric entry, and the brutal radiation of deep space is very, very substantial. NASA hasn't announced a specific mission or timeline for a flight version just yet.
But the success of this project fundamentally changes the conversation about what robots can actually do. Which leaves us with this final thought. If an Earthbound prototype can do in just one single week what took our absolute best Mars rovers a whole decade to accomplish, what is the actual flight model going to discover when we finally unleash it in the uncharted shadows of the moon? It's an incredibly exciting prospect, and I, for one, cannot wait to find out. Thanks so much for joining me on this explainer, and keep looking up.